Hey John, so this is an overview of the ALU project I'm going to be working on. I'm going to try to keep this pretty brief because a previous version of this video went on for 20 minutes or so, so that's a bit excessive. So just let me know if I'm going too fast over something and didn't really touch on it, and I can elaborate on any part of this. So the ALU will be the component in the processor that implements addition, subtraction, multiplication, division, modulus on both integers and floating point numbers. It also does the logical operations like and, or, not, XOR, and so on. It will compare values for equality, not equals, greater than, less than, and so on. I'm going to do something quite a bit more simple than that. I'm just going to have this work on integers, no floating point values, and I'm going to restrict myself to just 8 bits instead of like 32 or 64. And I'm not going to do any multiplication or division or modulus. So just addition, subtraction, some logical operations, and checking for if things are equal, not equal, greater than or less than, or sorry, greater than or equal, less than or equal, and so on. So the way I'm going to do this is to have two input values. I want the user to be able to input two numbers, A and B. I'm going to keep those in their own registers. The way the user is going to interact with this is going to be through an array of LEDs, which I'm just showing with boxes here. So I was thinking something like this. Probably have them all the same color, but basically 8 LEDs that correspond to the 8 bits in any given register. And then associated with each of those LEDs will be a button, something kind of like this. So the user will press a button and it'll activate that LED. And that will probably be tied into this temporary register. So the user will toggle their number in binary, which they'll be able to see in the LEDs, and then they can save that by pressing another button like load A here, and that'll save whatever they've entered into this temporary register. It'll save it into register A. They can do the same for B. So now they've got two values. In this example I'm showing here 35 for B and 47 for A. And then when the user hits another button, calculate, a number of operations will be carried out, and then the results will be stored in 7 different output registers. So those are going to be addition, subtraction, and or, the bitwise ANDing of both A and B, or the ORing of both A and B. Not A, the bits will be flipped for A, the bits will be flipped for B. And then finally, I will compare A and B, and then so this last register is just going to hold flags that will correspond to whether or not A is equal to B, or A is not equal to B, or A is greater than B, A is greater or equal to B, A is less than B, and A is less than or equal to B. So these bits will each correspond to those comparisons. There is also going to be 2 more flags, which I'll talk about later, for overflow and negative. And then this last output register will be just tied directly to the LEDs. So the user can, after hitting the calculate button and all these registers hold the results, there'll be maybe buttons for each of these positions in memory. The user can click it, and that'll dump the contents of any given result into 7, output register 7, which will be tied to the LEDs. So they'll be able to see the result that way. Each register is going to be implemented with a D latch. It's basically an array of flip-flops. So how that works is you just give it a value. So here's a picture of that. You'll just each one of these positions in the chip corresponds to a bit. And so you just input a value for each of those, and then if this enable pen goes high, each of these lines here correspond to these pens on the chip, and we can just have a button tied to this enable. So the user would push the button, and that would save whatever values are coming in. And then, so for example, like 1D, the first bit, you can have a voltage going in here. You can click the button for enable to save it, and then you can also see what's in there by just looking at this other pin. So each bit has an input and an output. So that's how the registers will be implemented. So basically the major things to talk about here, though, are the addition and subtraction. So down here I have a simple adder circuit. So we can't add the whole all 8 bits at once. We have to sort of add one at a time. And bit 0 for A and bit 0 for B can be shown down here as just X and Y, and all their possible values are shown here. And so the way to implement an adder is to just basically add each bit. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2, which is going to be a 0 with a 1 carried over. And so what this is the XOR operation. This is the exclusive OR, where we get a 1 only when they're different. We get a 0 when they're the same. So that's the sum of 2 bits, and then there'll be another output for that, which is the carry. So there wasn't a carry for the other ones, but only when both are 1 do we get a carry. And so this is the AND. Only when X and Y are both 1 do we get a 1. So what we can do is XOR each of these, put the result here, and then AND them and carry over that to the next column and XOR those, put the result there, AND them, move it over, and so on. And that carry bit can just keep moving along the bits, and that'll give us our number. Now, if we try to add 2 numbers where the result's going to be so big it won't fit in 8 bits, we'll have an overflow. We'll get a carry on this final bit 7 will carry over, and that is what this OF flag is going to be for this overflow. So if you try to add 2 numbers and the result's too big, this will become a 1, indicating that the result here isn't correct. To implement the subtraction operation, we can just use an adder still, but what we can do is so if we're subtracting B from A, what we can do is keep A as it is, and then flip all the bits in B, add those together, and then add 1 to that. So that'll give us the result on our subtraction. So what we'll be able to do is take A, flip all the bits in B, add those, put the result in here, bit by bit, and then once that's finished, add 1 more to it, and that'll give us the subtraction, the result of the subtraction. Now that can also have the situation of a carry forward to where it overflows on the last bit. If we have an overflow on a subtraction, that means that the number is positive. In this case, we're subtracting 35 from 47, so the result is a positive 12. So that means we had an overflow there. That means that this number is not negative, so that's a 0 in this case. If there was not an overflow, it would mean that this bit would go to 1, which would mean that the value was negative, i.e. we try to subtract a large number from a smaller number. So that's how the addition and subtraction will be implemented. The bitwise AND and ORs will be really straightforward. We'll just have chips similar to this that are just ANDs. You just put an input, AND it, and the output comes out, and you can just go bit by bit for AND, OR. Nodding is just flipping the bits. The comparisons are going to be a little bit more tricky. For equality, to check if 2 things are equal, we can come back to this XOR operation where we can see here where we get a 0 if they're the same. Well, what we can do is just flip the bits on an XOR to make an XNOR, which would be this. We're just flipping these bits. So if they're the same, whether they're 0 or 1, we get a 1, and if they're different, we get a 0. So we can XNOR these one by one, keep that maybe in a temporary location, then AND all those. And if those are all ones, the AND operation will be a 1, and that would be a 1 there. In this case, they're not equal, so we get a 0. For the not equals, we can just flip that bit for that one. I'm not sure how I'm going to do the greater than or equal, or greater than equal, less than equal operations. I'll have to look more into that. But that's the basic idea for the ALU, and I'll make a video once I get this thing together and working. See you later. Bye.